So next we're going to look at feature engineering. Feature engineering is often what matters most in data science and what data scientists spend most of their time doing. In fact, one of the superstars of machine learning said coming up with features is difficult, time-consuming, requires expert knowledge, but applied machine learning is basically feature engineering. So feature engineering. Not all features are of equal importance. Some features may not be necessary at all. Some features may be misleading. And all algorithms generalize to weighted methods, weighted nearest neighbors, both in how we compare neighbors and in how we make predictions. Which features should we use and how should we use them? How are features interrelated, giving us a topology. So feature engineering is essential. And it's usually based on domain knowledge. And the phrase domain knowledge means the scientific or technical context. Feature engineering is the use of domain knowledge to create and modify features so that algorithms work. Feature engineering in a physics application tends to require a physics background. Feature engineering in a financial application requires a finance background. Because algorithms are not scientists. Because a big data set tells many stories, but an application is interested in only one of those stories. Most data scientists spend most of their time in most of their applications doing feature engineering. And feature engineering uses metrics. Anytime you modify a set of data, you should measure both how and how much it was modified. Results could be due to your modifications rather than to the data itself. For example, if you impute missing values with a global mean, which is that you just average the entire data set and that number is used in place of any missing values, then any regression algorithm you use is going to be biased toward that global mean. But how big is that bias? Can it be safely ignored? Maybe it's tiny and really doesn't matter, or maybe it's influencing and biasing your entire application. That is, feature engineering is domain-driven feature modification that is guided and assessed by metrics. So here's some basic feature engineering that we've already seen, but I'm just giving you a review in the feature engineering context. For example, imputing missing values. Well, how do we do that? Well, we use supervised learning plus a metric. So for example, the training data is the data that has no missing values. And we tend to use regression, and we validate that with correlation, error, variance, that sort of thing. Rescaling or standardization. Now, actually, if it's just a change in the units, from example, miles instead of feet, then we can just do it. But otherwise, we want to test it using regression metrics. Log or linear transformations, modify data with more features than needed, for example, images. For example, principal components analysis with their own variance and confidence scores. For categorical data, we use one-hot encoding. So we can test with multi-class confusion matrix and related metrics. Grouping and splitting, rearranging the data so that features better reflect the domain relationship to the application. Typically, a data scientist in a given field uses domain knowledge in this case, and there are metrics associated with that. You may engineer an entire data set. For example, numerical representations of unstructured data, vector representations. We saw the TF-IDF, count tables of text, sparse key value pairs. And often we use precision and recall when we look at these kinds of things. Generating new features. Often we want to transform two variables that are important in a given context. So regression with regularization and information criteria. We'll actually look at these later. And unsupervised learning, including structure native to the data. Clustering, network representations, graph metrics, homogeneity, completeness, so on and so forth. So let's look at some examples. So clustering and homogeneity. You see, if a data set clusters into two components, one which is all positively labeled and the other which is all negatively labeled, then your clustering algorithm is a classifier. So here we have clusters, and the clustering is sufficient if the clusters are labeled positive or negative, in this case pass or fail, according to the clusters. But this only works because the data had a simple topology. In other words, it split into two label homogeneous subsets. Homogeneity is a similarity score between actual labels and labels predicted by clustering. The closer you are to one, the more clustering implies classification. The clusters may be well defined, however, but actual labels may not be related to the clusters. Here's an example with a homogeneity score of only 0.3689. And you can see, even though the data clusters, the labels are not with respect to the clusters. So topologies are often, but not always, far more complex than clusters of homogeneous blobs. And yet, sometimes, such clusters are quite useful. For example, let's look at the Palmer penguins dataset. A dataset comprising various measurements of 3 different penguin species, Adelaide, Gentoo, and Chinstrap. So this came out of a rigorous study from 2007 to 2009 by Dr. Kristen Gorman and her team. And our goal initially is we want to classify Gentoo versus not Gentoo, the others. We have 4 features: the bill length, the bill depth, the flipper length, and the body mass. And here you can see comparisons of the features pairwise. But notice we have wildly different scalings. So body mass is 3,000 to 7,000 grams, whereas bill length is 30 to 70. So here we have done what's called a maximum absolute scaling. And now we can see that in the upper right corner, that certainly has a homogeneity of 1. The clusters are with respect to the labels, or the labels are with respect to the clusters. On the other hand, over here on the far right, we can see that we have homogeneity close to 1, but we have some mixing of the labels. And of course, in the lower left, that's definitely low homogeneity. And there may only be 1 cluster, and the labels are just labeling different parts of a single cluster. So sure, we can classify Gentoo versus others by simply comparing, for example, flipper length to bill depth. But the scientists already know this. You see, they're the ones that selected these features. So while we can certainly do this with the data, they sort of already knew how to do this. And that's why they came up with these features. The real task is classifying the Adelaide versus the Chinstrap. But the scientists are going to need help with this task. They've provided meaningful features, but the features are not sufficient taken individually. Can we engineer new features that the scientists can use instead? Well, here we have, again, pairwise plots, and you can see that in most of these, the homogeneity is close to 0. Lots of overlap of the labels, and only single clusters. Fortunately, over here on the far left, we have some hope. We can see that these are almost linearly separable. So we're going to apply logistic regression to bill length, bill depth, flipper length, and body mass. The accuracy turns out to be 0.99. The area under the receiver operating characteristic curve is very close to 1. And we find out that the best model, we don't even fit the intercept. And this gives us a new analytic beta 1 times bill length plus beta 2 times bill depth plus beta 3 times flipper length plus beta 4 times body mass. And that if the analytic is greater than 0, it's chin strap, and if the analytic is less than 0, it's Adelaide. So we have something that is a new feature, something that scientists could use to better inform their study of penguins. What about the sex, island, and year? We didn't use those. But incorporating them will produce a different model. Is it a better model? Well, we don't know. You see, ultimately in feature engineering, the question is, how do we select the best model from two or more models based on the same data? There are two important methods in model selection. There's comparisons via metrics, especially precision and recall, and there's what's known as information criteria. So adjusting performance measures to account for differing model complexities. We'll see that in a later video. Often you use both in the same application. So let's look at precision and recall and why it can measure classifier performance. So remember, this is what a realistic confusion matrix looks like, a small epsilon and a small delta that keep us from having a perfect confusion matrix. Recall is the true positive rate, which is TP over capital P, which is P minus delta over P in our realistic confusion matrix. And that's 1 minus delta over capital P. The false positive rate is the false positive over capital N, which is epsilon over N. Precision is the fraction of observations classified as positive, capital TP plus FP, that are actually positive, TP. And it's TP over TP plus FP, which I can divide top and the bottom by the TP and get 1 over 1 plus FP over TP, which is 1 over 1 plus epsilon, capital P minus delta, that quantity, to the negative 1. So here's my precision, my recall, and my false positive rate. If precision is approximately 1 and recall is approximately 1, well, let's see what happens. The denominator would have to be approximately 1. That means epsilon P minus delta quantity to the negative 1 is approximately 0. And if recall is approximately 1, then delta over P is approximately 0. So if precision is approximately 1 and recall is approximately 1, then both delta and epsilon are small compared to capital P. And if the false positive rate is also close to 0, then epsilon is small compared to capital N. So for example, if we have a totally positive classifier, the precision, here we've got P over capital P plus N, and if we have a balanced data set, about the same number of positives and negatives, means the precision is a half. The coin toss classifier is TP over TP plus FP, but it's 1/2 over capital P plus capital N. And if P is approximately N, balanced data set, precision is about 1/4. And in the first video, we saw a tunable classifier, and it turns out its precision was about 72.9%. Now, also, we tend to use precision and recall together, and that leads us to the F1 matrix. Recall, the rate at which a classifier rates positive samples as positive. Precision, the rate at which a classifier does not label as positive a sample that is negative. The F1 score is the harmonic mean of precision and recall. And the weighted harmonic mean is F beta, and if beta is equal to 1, we just get the usual F1 score. So suppose we had T observations. Recall is true positive rate, TP over P, precision, TP over TP plus FP. And we tend to use these for validation or testing of a binary classifier. If we had an extremely ideal classifier, then TP would be capital P, FP would be 0, recall would be 1, and precision would be 1. We had an extremely positive classifier, then capital TP is P, capital FP is N, the recall would be 1, and the precision would be capital P over capital T, where here T is the number of observations. And we had an extremely negative classifier. If all capital T observations are classified as negative, well, unfortunately, we're going to be dividing by 0. So therefore, this is indeterminate. So instead, we talk about a nearly negative classifier. If there's one true positive and all the false positives are 0, in other words, we've made one positive prediction and it's correct, then recall is 1 over capital P, which if capital P is large is approximately 0, and precision is equal to 1. So suppose we have T observations. We're going to look at what's called the precision recall curve, PRC. Remember that the 1, 1 is the ideal classifier. That would be where recall and precision, horizontal and vertical axes, are both equal to 1. R and S, this is our actual recall and our actual precision for a given binary classifier. Extremely positive, where recall is 1 and we have the precision is capital P over capital T. Nearly negative is a recall of 0 and precision of 1. And we tend to connect these points by line segment so that precision is a function of recall. But usually we do this with a predictive model where we have actual labels, but then we have a probability of a label being positive. And we create a bunch of thresholds going from a low of 0 to a high of 1. And similar to the ROC curve, we have a classifier for each threshold, capital T. Notice here now capital T is going to be for the thresholds. And if the probability is greater than T, then we predict the observation is positive. And T ranges across the thresholds. So when T is 0, we have the extremely positive classifier. And when T is approximately 1, we have the nearly negative classifier. And as T moves through the thresholds, we end up with now a continuous curve, a different point for every threshold. The best is going to be the one that's closest to the ideal. And the ideal precision recall curve would be where we had a precision of 1 as the recall increases. So a curve that looks something like that. And the closer the precision recall curve is to the ideal, the better. The area under the precision recall curve is between 0 and 1. And a high area under the precision recall curve implies both high precision and high recall. Often we also use an F1 score, harmonic mean of precision and recall, and the closer that score is to 1, the better. We also often use the geometric mean, and we'll see that in the notebooks of precision and recall. So let's look at an example of polynomial features. Suppose we have dose levels from 12 milligrams to 36 milligrams. The efficacy is 1 if we have success at that dose, and efficacy is 0 if the medicine was not effective at that dose. And here's an example of some dose response test data. Now, at dose level X, the model is the probability of effective is the logistic curve. And here you can see it, the logistic classifier. The accuracy turned out to be 0.74 for this test data. But what if we had just simply taken a whole bunch of powers of our dose levels, X, then we would get polynomial features. In this case, we would have an nth degree polynomial where above we only had a linear expression. And guess what? The accuracy in this case, it's a weird looking curve, if that's your opinion, but it's got an accuracy of 0.76. It's always tempting to add nonlinear terms. You'll always get better scores because the linear model is a special case of the polynomial model. So certainly you can get improvement over a special case from a more general case. But you rarely get better models. For instance, here is the precision recall curves for the linear model and the polynomial model. You can see that the linear model is actually a better model based on the measurements with the precision recall curve. Now, if a domain expert knows from the scientific context that polynomial and nonlinear terms are appropriate, then certainly you should add them. But polynomial features are both dangerous and useful. They lead to highly complex, low bias models that often overfit the training data, can be poor even if they don't overfit. But where the science calls for them, definitely use them. And we've only seen a few metrics. As the course continues, we'll see more metrics, some more useful than those we've seen already. Algorithms differ primarily in how they use the data available to them. We'll see exception to that with neural networks later. Metrics, therefore, are at the heart of data science. The ability to assess outcomes is at least as important as the ability to produce outcomes. A well-assessed, simple algorithm is often sufficient. Therefore, we use metrics because they're also at the heart of feature engineering.